Try to answer this question. Which of these travels faster through space? I'll be honest, this is a trick question. The correct answer is not one of the options that I've given. The correct answer would be that they all have the same speed. The reason why is that all of these options are just different types of light. If you've never heard X-rays or gamma rays referred to as light before, it'll make better sense if we address this question: what is light? To answer this question, I need to give a short overview of an electric field. This image is showing a charged electrode. It's basically just a piece of metal that either has more electrons than protons if it's negatively charged, or more protons than electrons if it's positively charged. What you're seeing in this sort of fuzzy picture around this is this electrode is surrounded by a thin layer of oil, and then there is a bunch of pepper flakes that were sprinkled onto the oil. And you can see a definite pattern emerged from the way the pepper flakes oriented themselves and aligned themselves. This pattern that you're seeing is a representation of an electric field surrounding this charged electrode. So an electric field is simply an alteration of the space surrounding a charged object. Now, a lot of times we don't even notice electric fields. When you really notice electric field is when you have charged particles. Charged objects feel a force from an electric field. So for example, let's say this electrode has a positive charge to it. If I were to place two oppositely charged objects near this electrode, so let's say one has a positive charge and one has a negative charge, these charges are going to feel different forces. It would be something like this. The negative charge was attracted to the positive electrode, which is why we say that opposite charges attract. The positive charge was repelled by the positively charged electrode, which is why it was pushed away from it. The two charged objects were really just reacting to the electric field that occupied the space I placed them in. Here I'm showing two electrodes, and they have the same charge. You can see by the way the electric field seems to blend together very smoothly. If I were to place another charged object, let's say right here, the way that charge would react depends on the total combined electric field at that point. Here I'm showing a bar magnet. You've probably seen one of these, or just a magnet in general. On the edges of this bar magnet are iron filings, and what I want to point out is the unique pattern that they align themselves in. And maybe it's not so clear in this picture. It's a little more clear here. Look at how distinct that pattern is. When you spread the iron filings all around the magnet, you can see that it's not just right there close to the edge that this effect happens. You can see a definite pattern that's developed all around the magnet. What we're seeing is a representation of the magnetic field. And similar to an electric field, I'll define it as an alteration of the space surrounding a magnet. Magnets always have two poles. We usually call those the North Pole and the South Pole. And how those relate to the magnetic field, we say that the magnetic field lines come out of the North Pole and go into the South Pole. That's why we see this nice curvature between the poles. Here I have an image of two bar magnets, and the poles in this case must be opposite because we're seeing this nice smooth blend of magnetic fields. So it's got to come out of a North Pole and enter into a South Pole, and it's only going to do that smoothly if they're opposite like this. In this image, you can see that the magnetic field lines are actually repelled by each other. There's not a smooth blend, they're curving away from each other. This indicates that these two poles must be the same. Now, I don't know if it's north and north or south and south, but they're definitely the same because there's a repulsion. There's not a smooth transition between the magnetic field lines. You might be wondering, what does electric and magnetic fields have to do with light? Wasn't that the purpose of this video, to explain light? Well, it turns out that these fields are the key to understanding light. There's a very important observation that I need to explain that will really tie all of this together. A changing electric field creates a magnetic field. Turns out that this is also reversible. A changing magnetic field creates an electric field. These two observations are the key, really the keys to understanding light. So here I have a cartoon image of a bar magnet, and these lines are representing the magnetic field. Okay, so we saw this representation when we sprinkled iron filings around the magnet, so it's not too hard to imagine these lines. I mentioned earlier that the field lines come out of north, the north end, and go into the south end. For magnetic field lines like this, the closer they are together, the stronger the strength of the magnetic field. So close to the magnet, it's a strong field, and I'm sure you've used a magnet at some point in your life and know that when magnets are close together, there's a strong attraction or repulsion, but when you move them apart, it quickly dies away. So that's what we're seeing here. The wider these lines become, the weaker the field. Now, one thing that's not really represented well in this is that the magnetic field doesn't just end at some abrupt point in a square pattern like this. The field actually emanates all around. It just gets much weaker the further away you are from the magnet. So if I was to consider this point over here, that magnetic field would be pretty weak. And so the field lines, if I were to represent those, would be spread out quite a bit at this point. Okay, well, our focus just a minute ago was about changing magnetic fields. So a changing magnetic field creates an electric field. So I want to show you a way to represent changing magnetic fields. Turns out the easiest way to change the magnetic field of this bar magnet is to just simply move the bar magnet. So I'll kind of show you an example of that. As this bar magnet is getting closer, the magnetic field is increasing in strength. Right now it would be the strongest, and then now it's getting weaker and weaker as the bar magnet moves away. So that's an easy demonstration of a changing magnetic field. What that means is while the magnetic field was changing in this area, an electric field was being generated. Now, normally we don't ever notice the electric field that's being generated when you're just moving a bar magnet because we don't have charged objects that are reacting to it. So to notice the electric field that's being created by a changing magnetic field, you need charged objects. And the easiest way to do that is to just get wire. So imagine this is a coil of copper wire. Copper is a conductor, meaning there's lots of free electrons inside the metal. Electrons are charged objects, and in this case I call them free electrons because they're not bonded to any specific atom. So when an electric field is created, in the region of those free electrons, it pushes them around. When electrons start being pushed around and moving around, we create a flow of electrons. A flow of electrons is called an electric current. So if we want to create current in a wire, what we actually do is we create an electric field, and then that electric field starts to push the electrons around. So I'm going to say that an electric field in a conducting wire produces current. One way to create an electric field is to use a changing magnetic field. So in this case, I can create that changing magnetic field by just simply moving that bar magnet around. The key is that the magnetic field has to be changing. So that's why I keep moving it back and forth in this case. All right, but if I'm using a changing magnetic field to create an electric field, that electric field that's being created is also changing. So if the electric field is changing, and that's what we use to create current, then we can say that a changing electric field would produce a changing current. So there's going to be current in this wire, but it's going to be changing back and forth. This is a fun demonstration that I always do in class, and it's something that when you see it in person, it's a lot more interesting. I can't do that with you now, of course, but I did find a good YouTube clip that explains this exact same principle. The device you see on the table in front of this gentleman is a conducting coil. Just think of it as a bunch of copper wires wrapped together. There's no current in this coil. It's not hooked up to a power supply or a battery. The wires that you see coming off of it are hooked up to a device known as a galvanometer. That's just a fancy name for a device that measures current. So right now the reading is at 0, meaning there's no current in the coil. In his hand, he's holding a bar magnet. What he's going to do is, just like my animation, he's going to move that bar magnet around, which is going to create a changing magnetic field in the region of this conducting coil. So let's watch his explanation.
You can see that the reading on the galvanometer, which measures current, says 0. Now, I have a bar magnet with a north and south pole. And when I move the bar magnet through the coils, you'll notice that on the galvanometer we'll read some sort of current. But the current doesn't stay that way too long because it quickly moves back to 0. And that's because I'm no longer changing the magnetic field through the set of coils. But now when I remove the bar magnet through the coils the opposite way, the reading on the galvanometer goes in the opposite direction. So it's setting up a voltage to oppose the change in magnetic flux.
Okay, so right at the end there, he threw out some words that we won't have time to cover. But he demonstrated that you get a current when you change the magnetic field, but the key is that you have to be changing the magnetic field. So as long as it's changing, you'll get a current, and that current's going to react depending on which way you're changing the field. So you're probably wondering, what does this have to do with light? Wasn't that the original point of this video? It turns out this has everything to do with light. I've discussed electromagnetic waves in previous videos. All forms of light are just some version of an electromagnetic wave. The only thing that distinguishes the different types are their wavelengths and frequencies. What actually waves in an electromagnetic wave is the intensity or strength of the electric field and the magnetic field, which is what this image is trying to demonstrate. So let's look through this carefully. Let's start right here, and what they're trying to represent is that as this curve increases, they're saying that the strength of the electric field is increasing. Well, that increasing electric field is a changing electric field, which means that it's generating a changing magnetic field. So that magnetic field is increasing as well. Eventually, the electric field will reach some maximum strength and start to decrease in intensity. That is, again, a changing electric field, which creates a changing magnetic field, which is also decreasing. Okay, but the interesting thing about this relationship is it's reversible. So if a magnetic field is changing, then that should be creating an electric field, okay, which is kind of what we're representing here. But that is going to be creating an electric field that changes. That changing electric field should then be creating a changing magnetic field. But that changing magnetic field is going to create a changing electric field, and that electric field is going to create a changing magnetic field. So you can see how that cycles just back and forth. It's a continuous, unending cycle. That's what an electromagnetic wave is, and that's why it can travel through a vacuum. It can travel through empty space for as far as it can go until it runs into something. because it's just a non-ending transfer of electric and magnetic field energy. This perfect interaction requires that all electromagnetic waves travel at the same speed in a vacuum. The type of electromagnetic waves that we're most familiar with as humans is visible light. And that ranges from red to violet in terms of color. We can distinguish between these colors by their wavelengths. Red has the longest wavelength at about 700 nanometers. Violet is the shortest wavelength at about 400 nanometers. And green is right in the middle at about 550 nanometers. All of these waves are traveling at the same speed. If you remember, wave speed can be defined as the wavelength multiplied by the frequency, which means we can define the frequency as the wave speed divided by the wavelength. All three of these waves have the same wave speed, so by looking at the wavelength, we can make a direct comparison of their frequency as well. The smallest wavelength is going to have the highest frequency, as you can see here for violet. So in the same amount of distance as these green and red waves, violet has more oscillations in that distance, which is why we say it has higher frequency. Red, with the longest wavelength, would have the lowest frequency. So mathematically, because wavelength is in the denominator. Right, we can kind of tie this all together with the other types of electromagnetic waves with what's known as the electromagnetic spectrum. So that includes everything between radio waves and gamma rays. You can see them listed here. All right, what this graph is showing is it's trying to show you a representation of wavelength for the different types of electromagnetic waves. I do need to point out, though, that this figure is not trying to represent one single wave. It's just a visual way to think, oh, radio waves must have longer wavelength than infrared, and then gamma rays up here has the shortest wavelength. All of these electromagnetic waves can be described as light. The light that we specifically see as humans is distinguished by the word visible. We call that visible light. But in science, we often refer to all of these as just light in general. They all have the same wave speed, so we can directly relate their frequency by their wavelength. So if gamma has the smallest wavelength, that means it has the highest frequency. That's the numbers that you're seeing at the bottom here. So 10 to the 18 is 1 million trillion. So what that means is a gamma ray has 1 million trillion oscillations each second. That's an unimaginably big number. It's hard to even imagine what that would even be like. Notice that radio waves with the much longer wavelength have a much shorter frequency, but that's still 10,000. 10 to the 4 is 10,000. So that means radio waves are still oscillating around 10,000 times each second, what we call a hertz. Frequency is a useful quantity to understand for electromagnetic waves because the energy of an electromagnetic wave is related to its frequency. So if we look at gamma rays up there, because they have the largest frequency, that means they have the highest energy. That's why it's dangerous to be exposed to gamma rays. They're harmful to humans. At best, if you're exposed to gamma rays, you'll turn into this. If you don't know who this guy is, I just feel sorry for you. Now, maybe you know him better like this nowadays. Okay, but the backstory of this guy is that he was exposed to gamma rays, and so that's where he gained his powers. In real life, if you're exposed to enough gamma rays, you'll most likely just end up dead. If we go lower in the frequency range, visible light, we are exposed to visible light all day, and there's not any adverse effects from that. Now, it is true that if you sit in the sun, you'll get sunburned, but that's not because of visible light, that's because of ultraviolet light, or UV light. The sun is emitting both, and it's the ultraviolet that actually causes the sunburn. So I want to focus here on visible light for a minute. If you notice, visible light is just a small portion of the entire electromagnetic spectrum. What that means is all of the colors that we see, from red to violet, those are all bunched into this little tiny area compared to the rest of the entire spectrum. So I've always found that fascinating that as humans we can only see just a small percentage of the total possible range of electromagnetic waves. So I want to address this question. Why does it make sense for our eyes to only be sensitive to a small portion of the electromagnetic spectrum? Well, how we make sense of that is to analyze what type of light are we mostly exposed to as humans from the beginning of our history till now. Well, it comes from this guy, the sun. The sun is outputting all types of electromagnetic waves. So X-rays, even radio waves. If we measure the intensity of each type of wave, it's not actually the same. So the amount of X-rays coming from the sun are not equal to the amount of ultraviolet light coming from the sun. How we classify that is we use a device known as a spectrometer, and that information is compiled into something that looks like this. This is known as a spectrum. Okay, it's showing the intensity or the energy in coming from the sun. We're looking at the sun specifically. So this is showing the energy coming from the sun at specific wavelengths. So it does emit light at all wavelengths, but there's a definite peak in a certain range of wavelength. And it's shown here. It's between about 400 and 700 nanometers. And if you remember from several conversations, that is the range that we call visible light. So our sun, by far, emits the most amount of energy in the form of what we call visible light. Since that's the primary light that we've been exposed through for all of human existence, it makes sense that we would be most sensitive to that light. All right, we're going to take a little break here. I hope you enjoyed this introduction to light. For some reason, I just find this topic fascinating. In the next video, we'll explore how light interacts with matter specifically.